Hello, everybody. Welcome. I'd like to, welcome you guys here for the section on calculus, starting at chapter 2. So, for this section, we are going to first start by talking about what is it that we are trying to achieve by the end of this chapter. So then that way you can get an overview, and then that way it's kind of like a better perspective. So here is going to be the starter of it. Now, I first need to start by introducing or defining a terminology that you might have heard back in geometry days, and that is going to be a tangent line over here. So, our formal definition for a tangent line is that a line that touches or intersects with the given curve at the point of tangency locally. So, what that means is you can see that I have a curve underneath over here. We can go ahead and call f of x or y is equal to f of x. And if I choose any point on this curve, let's say somewhere like over here, the tangent line would then be a line that touches that curve just at that one single point over here and nowhere else. Now, if you actually take that little small portion right there and I guess like magnify it so you can see it like as a bigger picture, then what happens is that you can see that it's going to touch the curve, as I said, at that one single point and nowhere else. And if I take that picture and blow it up even further, one would even say that the curve, if magnified enough, is almost just like exactly the same as the tangent line over here. But still, nonetheless, it's still going to touch at only one single point locally and nowhere else then. Now, I say the word locally because you technically have a line that could touch the curve somewhere else further away. So, for example, if I put the point over here, you can see that its tangent line will eventually touch the curve somewhere else further away. And that's okay. Okay, so long as if you magnify that small little part and that curve and that line is only touching that one single point, then that's fine then. Then that's how we define the tangent line then. So what I would like to do is by the end of this chapter, be able to solve for what is the slope of the tangent line for any given curve. Okay, so let me repeat it one more time. I would like to be able to solve for what is the slope, or maybe even the equation of a line, of the tangent line at any single point of the curve. So here is an example of a problem that we might encounter. So here it says find the equation of the tangent line at x equals to 1 for the curve y is equal to f of x at x is equal to, x to the third. So if I can, I guess, give you like a visual as to what I'm asking for. So here is the graph of y is equal to x to the third, which is going to be a cubic function. Looks something like this. And if I go to 1 over here, I want to find out, and I draw the point of tangency, I want to find out what is this line of tangency that's over here. So that's going to be our question. Now, is it going to be only one single line? And the answer is yes. There's only going to be one single tangent line for any given point. It's not going to be any other one, okay? So let's go ahead and try to figure that out. So what I can do is I can introduce a secant line in order to get an estimate as to what the tangent line is. Now, for those of you guys that aren't familiar with the term, the secant line is basically saying, hey, I'm going to take a line that intersects the curve at 2 points, because if you think about how to solve for the slope, right, usually what you need is 2 points. What you need are 2 points, 2 points preferably on the curve. So what I can do is maybe what I can say is let's go ahead and do the following then. The slope is going to be the change of y over the change of x. Okay. Now, if that's the case, then why don't I find a point that's nearby, so then that way I can see what the slope is approximately. So for example, maybe I can say let x equal to 1.1, right? Because within that window, you can see that if I draw the two lines, if I draw the line right there, that secant line is almost kind of like the same slope as the tangent line. So here's what I'm going to solve for. I'm going to solve for f of 1.1 minus f of 1, and then all divided by 1.1 minus 1. So like we said, change of y over the change of x, where the points that I'm getting, the 2 points that I'm getting, they're both going to be on the curve. So if I plug those into the calculator and then see what I get, that'll give me an idea then, okay? So let's go ahead and see what that is first. So if I go to my calculator over here, let me go ahead and clear this up for a second. Let's see, we have x cubed as our function, right, if I remember correctly. And here's a nice thing too, if you guys don't know about this little neat trick, your calculator, you can call your function as kind of like an f of x or g of x function. So if you go to vars, and then you go to y vars over here, where you create, where you select the function, if you put a parentheses around it afterwards, that's kind of like saying f of 1.1. So then that means I'm plugging in 1.1 for x. Then I'm going to go ahead and subtract, doing the same thing, right? Go to vars and then y vars, and then going to select y's of 1, and then going to put that parentheses right there. So then now we have y's of 1.1 minus y's of 1. So it's kind of like saying f of 1.1 minus f of 1, right? That's what we wanted to begin with. And I am now going to go ahead and put a little bit more parentheses over here just to kind of make sure that we can actually write the fractions afterwards. So close that parentheses, divided by 1.1 minus 1 then. So what we get is 3.31. So if I go back to the screen right here, then that means that my slope is approximately 3.31 then. Now, unfortunately, that is not good enough because we're using the secant line in order to estimate the tangent line. But this does give me something to kind of work with. Well, what if I close that gap a little bit and say f of 1.01 minus f of 1, all divided by 1.01 minus 1 instead. So notice how my interval, right, between the x values are getting smaller so that the 2 points are getting closer and closer to each other. Well, if I put those in the calculator, just go back to what we were over here. Let's go and make this modification. I'm going to push second enter, which allows me to go back to my previously input. And I'm going to modify it by putting a 1.01 over here. And then over here, I'm going to go ahead and put invisible and put in a 1.01 over here. And let's see, it looks like this time it's now giving me 3.0301. So that is now something that I like. 3.0301. So notice that it's now giving me something that's a little bit more and more accurate each time. Well, let's do this one more time because I don't want to get too repetitive. What if I now change it so that it's 1.001 minus f of 1, all divided by 1.001 minus 1. So notice again, each time we're basically making that gap a lot smaller and smaller and smaller, so then that way we have like a better and better and accurate estimate. So one more time, we're going to go back to the calculator, and we're going to go ahead and put second enter and change that one more time so that we're going to sneak in another 0 over here. And then I'm going to sneak in another 0 over here. And there we go. So it looks like it's going to be 3.003 this time. And so I'm going to put that in. So 3.003001. Now, we can do this as often as you need to. But the idea here is that sooner or later, you're going to notice a pattern. And that pattern is that the number is getting closer and closer to a finite value. And that finite value is basically going to be our tangent slope. Well, judging from what I'm seeing right here, it looks like that the number is getting closer and closer to 3 because it's basically decreasing, but it's to a point where it doesn't go below 3. So my guess is that the tangent slope is going to be equal to 3 then. Okay, so you can do this as many times as you need to in order to get a in order to get a value that you think is correct. If 3 times is enough, great. If 5 times is enough, great. It's all up to you, but you don't want to do too much work though if possible. Okay. Well, now that I have the slope, then I need to find out what's the equation of the line. And in calculus, we always try to use the point slope form because, well, that's the easiest form to actually manipulate algebraically and also to write down. So we know what the slope is, so that's great. The coordinate that we're working with is at x is equal to 1. So if I plug it back into the equation, right, then f of 1 is equal to 1. So that means the coordinate is going to be 1 runner here. So from the point slope form, okay, then our answer is going to be y minus 1 is equal to 3 multiplied by x minus 1. So that is going to be our equation of the tangent line then. Okay. All right, so now let's look at another problem which has kind of like a similar idea, but this time let's look at it as a kind of like a word problem over here. So here, Mr. Chan is sitting outside of the school in his white van passing out calculus problems to kids because, you know, that's what we can do. The table below shows how many kids came to the van. I didn't even give this a unit for that one. So it's supposed to be T minutes, right, after Mr. Chan started. So you can see the table below, how many kids came by during that specific time then. So for example, like say at 23 minutes, there were exactly 10 kids that came by. Whereas at 10 minutes, only 7 kids came by, and so on and so on and so on. Okay. Now, what I like to do is solve for the following. I want to solve for, or in this case, estimate what is the tangent slope at t is equal to 23. So using the same idea, what I can do is I can pick 2 points to estimate what the slope is. Now, unfortunately, unlike the first example, we don't have an equation to plug in. So that means we're forced to use a secant line in order to estimate the tangent line. So repeating that one more time, I need to use a secant line in order to estimate the tangent line because we don't have an equation to plug in. We don't have 23.1 or 22.9 or something like that. We only have 25 and 20. So then that means that we have to literally just solve for what we're given. So the estimate in this case, we can have 20, from the right-hand side, we can look at this right here, okay? We can say 2 minus 10 divided by 25 minus 23, right? Because I'm looking at the change of y divided by the change of t in this case, right? The change of a number of kids divided by a change of number of times. And if I divide it through, just kind of clean up the work, you're going to get negative 8 divided by, looks like it's going to be 2. So that means it's going to be negative 4. Now, the unit for this is supposed to be negative 4 kids per minute. So that means at that instantaneous time, I am going to be losing about 4 kids per minute, or I'm not going to have 4 kids less per minute in this case. Now, do I have to use the right-hand side from 25 to 23? The answer is no. You can actually use the left-hand side also. So another variation of this answer, right, using the same concept, I can use the left-hand side. So let me kind of write this out. This is going to be my right-hand side, okay? If I use the left-hand side, then this is what I'm going to get. I am going to look at 10 minus 5, and then, let's see, divided by 23 minus 20. So then that means I'm going to get 5 divided by 3. And in terms of units, that's going to be 5 kids per minute. Now, you can look at the two answers and you'll realize that, hey, you know what? They're completely different. And that's actually okay because remember, we only have a chart to work with. We don't actually have an actual equation. So at best, what we can do is just estimate, okay? And one more other one, if you guys can see it, instead of working on the right-hand side, instead of working on the left-hand side, hey, maybe we can just take the whole thing over here, you know, just all of the surrounding of t is equal to 23. So this last one is going to be kind of like a combination of both, right? This is going to be looking at from 23 to 20 because 23 is in the middle. So I can also say 2 minus 5 divided by 25 minus 20, and that's going to give me negative 3 divided by 5 then. And that's going to be in terms of kids per minute as well. Okay, so all of these 3 answers are acceptable. Now, what's most likely going to happen is if you're seeing this as like say multiple choice questions, they will probably tell you to use specifically the left-hand side, the right-hand side, or the average, like in this case, which is going to be both. But if they don't specify, like say this is a free response questions, you can technically use either one unless they tell you to. Okay. All right. Now, here it says explain the meaning of your answer in part A and provide the units. Well, I guess I actually provided the units already. It's the number of kids that you're going to be getting or losing per minute then at that instantaneous moment then. Okay. Yeah, so that's going to be our explanation and also the meaning of it. So if I kind of write this down, okay, kids per minute, okay. Sorry, let me just be a little bit more specific here. Okay, so let me just kind of write the whole thing out. It is the representing, okay, representing the rate at which kids are coming or going, okay, at that time of t is equal to 23 minutes then. And the unit for that, it was supposed to be in terms of kids per minute. Okay? All right. So now let's look at this last example over here, a word problem where I'm going to give you an actual equation. So a ball is thrown up from 6 feet from the ground, and its height can be determined by the function h of t over here, where t is the number of seconds after it was thrown. I want to evaluate what is h of 1.2 minus h of 8 divided by 1.2 minus 8. What is its units and its meaning for this problem? So this is very similar, if not exactly the same, as what we've been doing so far. If I'm asking for you to specifically solve for the change of y over the change of x, then that means I'm asking for you to solve for a rate. Now, this is a secant because you can see that there is a specific interval that we're using, and we're using two specific points. So if you're ever using a secant in this case, you're trying to find what is the average rate of change. Okay, so in this case, let me just kind of write that down first. Okay, so over here, we're solving for the average rate of change. Okay. And that's all because we actually have an interval for the change of y, and we also have an interval for the change of x. So what I'm going to do now is I'm going to go to my calculator, and I'm going to go ahead and write the equation in there. So negative 10 x squared plus 13x, and then plus 6. And I'm going to go to second quit over here, and we'll do exactly the same thing as what we did earlier. So I'm going to go in parentheses. I'm going to go to vars so I can get the function. And it's going to be y1. I'm plugging in 1.2 into it. And then minus plugging into the equation, I think it was 0.8, right? So 0.8. And then close the parentheses, divided by 1.2 minus 8, and then close the parentheses. So what I'm getting here is 0.412 approximately. So let me go ahead and put that down over here. So h of 2, or h of 1.2 minus h of 0.8 divided by 1.2 minus 0.8 is approximately equal to 0. I think it was 411. I can't remember. Yes, 411. Okay, oops, wrong button. 412, just so that we round it off to 3 decimal places. And by the way, all AP tests, they will ask you to round to 3 decimal places 99% of the time. Let's see, so that's going to be our average rate of change, and the unit for this, so let's see, the change in height over the change in time, so that means it's going to be feet per, looks like, what was it, seconds? I think that was the unit that I was using. Okay, so here, once again, just to conclude, this right here solves for the average rate of change, right, between the time t is equal to 0.8 seconds to t is equal to 1.2 seconds. Okay, and the unit right there is going to be feet per second, and the number is supposed to be 0.412 then. Okay, all right, last part right here, estimate the instantaneous rate of change of the ball at t is equal to 1 after it has been thrown. Well, this right here, the instantaneous rate of change, the difference between the instantaneous rate of change and the average rate of change is that instantaneous, that's like saying what is the tangent. Whereas the average right here, that's like saying what is the secant. So what that means is if I want to solve for tangent, I have to go back to what I did back in number 1 over here. That is to say, go to t is equal to 1, and I'm going to plug in 2 points that are getting closer and closer and closer. I'm sorry, plug in another point that's getting closer and closer and closer to 1, and then get an estimate to see what the slope is going to be. So here we go. Let's go ahead and do that then. So just like before, okay, I am going to go ahead and maybe plug in the following then. So let's say this time I'm going to go ahead and use h of 1.1 minus h of 1, and all that divided by 1.1. Oh, sorry, let me go ahead and erase that, make it a little bit nicer looking. 1.1 minus 1 then. Okay, so let's get an estimate for that one. So going back over here, we're going to push second, enter. Okay, and let's see, change this guy to a 1.1, change this guy to a 1. Then we are going to change this into a 1, and this also to a 1.1. So we're going to get a -8 in this case, okay? That's a pretty bad estimate, but it'll give us something to begin with. Now we're going to take the interval and make it a little bit smaller, so then that way we get a gauge as to what that number is approaching towards. What's that tangent slope going to be? So go back to, oops, sorry. Let's see, go back to the calculator, second, enter. Okay, go back to my previous command, sneak in a 0 over here. And you can see how this is very helpful right here because I don't have to re-enter everything every single time. So this time I'm getting -7.1. So let's see, I'm going to put in -7.1 then. And let's just do it maybe one more time if it helps to see where that is approaching, because I definitely don't see it just yet. And again, you can do it as many times as you need to until you feel comfortable with the exact answer, okay? Okay, so let's see. We're going to go second, enter. So this time sneak in another 0. Oops, sorry, that's not a 0 right here. That's a, there you go, there's a 0. And over here, let's go ahead and sneak in another 0. And looks like it's -7.01. Okay, so it's -7.01. And by now you can probably see that, oh yeah, looks like it's getting closer and closer to -7, and that's going to be our answer. Okay, so as I said, do as many times as you need to a point where you can see what that number is getting closer and closer to. So in the very end, our answer is going to be -7, right? Because that's what it's getting closer and closer to. And the rate in this case, again, it's going to be feet per second, because feet is supposed to be the unit for y, and second is supposed to be the unit for the time then. So that's going to be my instantaneous rate of change, meaning how fast the ball in this case is falling because it's negative at t is equal to 1. All right. All right, so hopefully that will be insightful for you guys, and I'll see you next time then, okay? Take care.